like to welcome you all back to the Design on Cloud Pavilion, which has been sponsored by Google Cloud and Microsoft. Hope everyone had a great lunch and has been having a great week. We still have a few great presentations to go this afternoon. I'm particularly pleased to announce our next speaker, who is a longtime colleague of mine from my days at TI. He and I go way back, and I was really excited that he was able to present at this year's DAC. He is a member of group technical staff at Texas Instruments. Can you please give a warm welcome to Mitch Richling?
I was kind of expecting a story. All right. So last year I gave a talk at DAC about cloud TCOs, how to decide when it was cheaper to use the external cloud versus internal resources. And a big part of that is getting multi-tenancy and job tenancy correctly. How many jobs do I run in a box? How many VMs do I run on a physical server? I glossed over that in my presentation last year, and I've been punished over the last year with people contacting me, asking me, how do you do that part? So I thought I'll come back and I'll talk about that part. So, outline of the talk. First we'll do a little bit of context, some thought experiments, then find out why the thought experiments don't work, a little bit of probability theory, and then we're going to compute some risk. Those are the steps that we generally use inside of TI anyway to get multi-tenancy right. So for context, a little bit of background about the numbers I'm going to be talking about. The first number is CPU utilization. That's the number at the top of the top output. What is the utilization of an entire server? A slot, I've stolen that from LSF. It's essentially an allocation for a job thread, a place for a job to run. Job runtime is simply the amount of time a job spends on a box. Take the finish time, subtract the dispatch time. That's the wall clock time or the job runtime. The reserved time is that same value multiplied by the number of slots reserved. So this is a measure of the amount of CPU resource that a job is reserved to run. CPU time, that's the amount of CPU time you actually use. The job may have been on a box for an hour, but it may have only used half an hour of CPU time. And job efficiency is the ratio of that CPU time divided by the reserved time. So it may have been on a box for 4 hours, me using 4 CPUs, but used 1 hour of CPU time in total. You divide those two, you get a percentage. These are the core numbers that I'm going to be talking about throughout the entire presentation. Now, when I was a kid, every simulation job was 100% efficient. It used exactly 1 CPU. There was no multi-threading. It was good. I also walked uphill both ways to school. Maybe that's a lie. But it was true that jobs were extraordinarily efficient. So efficient that the standard practice in, say, the year 2000 was to run with a slot-to-core ratio of 1. We would achieve utilization numbers in our farms of 99 to 100%. All of our resources were mostly consumed. But something horrible happened. That was this. It's the same curve that you see in the HPC industry as a whole, except in the larger HPC industry, we saw this curve happen about 10 years ago. We see it in EDA now. I don't have data going back to 2000, but I have it to 2004, and you see that job efficiency just linearly crashed. Started to peak back up in the early 2010s, and it's slowly climbing. You could write books about why this is happening. It doesn't really matter. All that matters to us is the reality of the fact that job efficiency is low. When we run with 1 slot per core, or when we run single tenancy, we waste a ton of resources. But at the same time, most people are really scared about running at a higher tenancy. What happens if those jobs interact badly? We've all gone through the thought process. I know I'm going to increase my system utilization. I know I'm going to increase throughput. This will make the bean counters in my company happy. This will make the engineers in my company happy. But if they interact badly, I create a risk that individual jobs may run slower. Depending on your company priorities, that may not be important, but for most of us, it is important. This whole presentation is about quantifying this risk. Because if we can quantify it and we can cap it, then we can pretend we're an insurance company or a casino. And we transform that scary question of higher slot to core values into a simple business analysis with business priorities and risk. So you can send it off to the actuarial people in your business analyst group, and they can make the decision about where to set that value. So our goal is simply to transform the question into a mathematical question about risk. So some thought experiments, sort of Einstein-esque. We're going to just dream through what would happen. But I warn you, these thought experiments are simple, and they won't lead us to a solution, but they will lead us to some insight. Okay? We're using simple averages in these thought experiments. So suppose you had a job efficiency in your farm of 90%, and your compute servers have 4 cores. So this is like 2003. In this world, we have 4 cores, we have 4 jobs in red, and a little bit of CPU left over, 10%. Our job efficiency was 90%, so our system utilization is capped at 90%. That's a mathematical truism. If you run with slot to core ratio of 1, the utilization in your farm is going to be essentially equal to the job efficiency in your farm. And of course, we're wasting 40% of a CPU. That is 10% on each of the 4 cores. There's not much I can do in that scenario. But if something changes, like the job efficiency were 80% instead of 90, still 4 cores. Here's the picture. We have a little bit more at the top of each CPU core. Of course, system utilization capped at 80, like I mentioned on the previous slide. We have 80% of the CPU wasted. But now we say, aha, 80%. That's exactly the amount of CPU capacity I needed to run a job. So if in this scenario, I put a 5th job on there, what would happen? In this case, the system utilization would go to 100, our throughput increases by 20%, and job runtime is not impacted. You get a bonus this year, right? Because you just got 20% of your compute farm added to your compute farm for free. Of course, we know this really doesn't work, and we'll get to that in a minute, but the idea is still valid. Here's, of course, the picture. The little green part is the extra job that we ran. Instead of changing the utilization, let's go back to our original scenario where we had 90% utilization or 90% efficiency, but now we have 12 cores instead of 4. Here's the picture. We have a lot of little white slivers at the top of each core, and yes, that's hexadecimal. We're still capped at 90%, just like we were in the first one, but now we have 1.2 CPUs wasted, right? Because we have 10% of 12 cores that we haven't been using. So we could go raise our slot to core ratio from 13 to 12. We get 97.5% utilization. We're still wasting 30% of a CPU per box. Our throughput improved by 7.5%, and runtime was not impacted. So what do we learn from the thought experiment? One is that there are 2 variables, the number of cores per box and the efficiency of the jobs that are running. These 2 things both play on top of each other. And, of course, the overall idea, which is if I have some CPU capacity left over, I try to run a job there until I hurt individual job runtime. Now, an optimist is going to look at what we just did, and they're going to say, hey, I saw that graph you put up. If job efficiency is 75%, I ought to be able to run 30% more cores, right? And I didn't use Grumpy Cat because, he's copywritten, but, the realist says no. Why? Because the realist realizes that our thought experiment was a little bit simple. We've all heard about the 6-foot statistician who drowned because he knew the average depth of the water was 5 feet. Averages kill. So let's talk about some ugliness in compute farms. The first ugliness is about those averages. Here's a single job. It's a 12-way job on 1 box with 12 cores. Notice it never really got above 75% utilization, but this job is like 5 days long. It spends almost a whole day down here in the doldrums, 25%, 50%. The rest of the time it spends at 75%. So the vulgarity here is that CPU utilization or job efficiency is not constant, even in a single job. To make matters worse, when I have multiple jobs on a system, it's not constant either. This red line is the CPU utilization of the box. The top of the black is where it would have been if those jobs had been 100% efficient. Notice we have a huge gap here, tiny little gap here. So in the normal day-to-day runtime of this box, we have terrible efficiency, we have actually pretty good efficiency. We can't just think in averages, but the idea is the same as we did in our thought experiment. Figure out how much CPU is left over and try to cram some extra jobs in there. There are also some other ugly things that get in the way. Scheduling policies do all kinds of crazy stuff in your farm. They may in fact lump jobs together of similar efficiency. Job chunking will do weird things to you too. They may pack systems onto a job until one machine is full and another machine is idle. And you can have the opposite happen. You can have some systems that aren't full at all, but the scheduler for some reason thinks they're full. All of those policies that we put into our DRM tools, that is distributed resource management tools, make the problem more complex. For now, I'm going to ignore this stuff and just think about how we work with the averages and the probabilities of what's going to happen. And we'll come back to that other stuff later. So the good news is that probability theory gives us a good number of tools to think about things that are more complex than averages. The second good news is that the kind of probability theory we need is not what you learn in PhD school, it's what you learn when you throw dice. And in fact, even if you never set up multi-tenancy on a compute farm, you may leave this presentation a better craps player, or, God forbid, a better Dungeons and Dragons player. So here's a die. That's the singular form of dice, a die. It has 6 sides. The probability of each face showing up when you throw it on the table is 1/6. Why is that? It's because there are 6 sides on the die, so there are 6 ways for it to land. The probability of one particular face landing up is 1 out of 6. If we throw 2 dice, let's put the first die here on the left, second die on the top, and we have the sum. So if I roll a 1 and a 1, I get a 2. Notice there are 36 ways for those 2 dice to land on the table. But also notice that the sums of the faces duplicate. For example, there are lots of ways to roll a 7. How do we get the probability from this table? Suppose you wanted to know the probability of rolling a 4. You count the number of ways you can roll a 4. There's 3 of them. You count the number of ways there are for the dice to land. There are 36, and you divide. So the probability of rolling a 4 is 1 out of 12. You repeat this for all the numbers, 2 up through 12. Get this little table. There's only one way to roll a 2, right? That is to roll a 1 and a 1. There's only one way to roll a 12. That is roll a 6 and a 6. Bunch of ways to roll a 7. It is 6 times more likely to roll a 7 than it is to roll a 2 or a 12. If you've ever played craps, 2, 7, and 12 are really special numbers. This is why. What if I roll 3 dice? Now this is getting fun. Let's put in the upper left-hand corner the value of the first die that I roll. Let's put here in the rows the second die that I roll. And in the columns the third die that I roll. There are 216 different ways for 3 dice to land. If I wanted to compute the probability of rolling a 10, I find all the 10s in the table. There are 27 of them. I divide by 216. The probability of rolling a 10 if I roll 3 dice is 1 out of 8. Do that for all of the possibilities. 3 is the smallest one because I can roll 3 ones. That's the lowest I can get, and an 18. Here are the probabilities. Notice it's kind of smooth. There is some deep, beautiful mathematics going on right here, and it's related to a thing in Stats 101 that you probably were exposed to called the central limit theorem. It's not an accident that this thing is starting to look smooth. So let's think about what we did from an algorithmic complexity standpoint. If I wanted to compute rolling dice, how hard is it? When I did 2 dice, it was 36 entries. I had to compute 6 squared things in a table, search, add, and divide. When I did 3 dice, it was 6 cubed. If I wanted to roll n 6-sided dice, the algorithmic complexity of this is 6 to the n. And unfortunately, we're not going to be rolling 6-sided dice later. So I'm rolling m-sided dice. The algorithmic complexity of what we've just done to compute n m-sided dice and get the probability distribution is of complexity m to the n. If you remember one thing from your algorithms class in college, it would be that If you have an algorithm of this complexity, you need a new algorithm. So let's think about a different way to do what we just did. First, a little refresher. I won't explain why, but I will repeat what the rules are. If you have two events and you want to know what the probability of them both occurring at the same time is, you multiply. Get two events, you want to know what the probability is of the first one happening or the second one happening or them both happening, you add. So, and is multiply, or is add. So this is exactly the same table we had when we threw two dice. I have my first die here, my second die here, and I've written the probability for each side. It's kind of silly because it's all 1 over 6, but it'll get more complicated later. Same up here. The probability of rolling this particular 6 is the probability of rolling that 4, which is 1 over 6, and that 2, which is 1 over 6. So the probability of getting this 4 and 2 is multiplying, so it's 1 over 6 squared. There are 1, 2, 3, 4, 5 ways to get a 6. The probability of one of these two things being hit, this is an or, this one or that one or that one or that one or that one, so I add. So the probability of rolling a 6 is 1 over 6 squared added up 5 times. Now, you may be shaking your head and saying, okay, that's a different way to do what we just did, but it seemed just as hard, maybe even harder than what we did before. But this method generalizes to dice that aren't fair. For example, if I went back to my 6-sided die and then a very unfair die that tends to roll a 3 most of the time when you roll it, what if I rolled these two dice together? The new algorithm, the new way of computing the probabilities works if I have an unfair die. Let's try to roll these two unfair die together. The probability of this 6 right here is rolling that 4 and that 2. 1/6 times 2/15. But the probability of this 6 is rolling that 3, which is 1/6, and this 3, which is 9 over 15. That's different. The probability of this event happening is different from the probability of this event happening. To get the probability of any of those 6s happening, it's an or again, so we add, and there it is. 1/45th, 1/45th, 1/10th, that's this one, and 1/45th. The probability of rolling that particular one of these 4 is going to be 1 over 6. So you might be shaking your head again and thinking, what does this mean? Here's the overall die. How does this help us roll lots of dice? Well, so as an aside, I put some code in here to show you the process we just did because, well, it may be fuzzy in your brain just listening to me talk about it and point at things. You can read the code and you'll know exactly what it does. It's terribly bad code. It actually constructs two matrices. It doesn't have to, but it's easy to read. So here's where you go if you're a little fuzzy on what we just did. But you might be thinking, okay, so I can roll loaded dice now, but how does this help me get a faster algorithm for doing in m-sided dice? Remember this? This was the probability distribution of throwing two dice, two fair 6-sided dice. What if I thought of this as instead of two fair dice being thrown, if I thought about it as one 11-sided die with faces labeled 2 through 12 and a really crazy probability for each face? In other words, what if this was a really crazy unfair die? Could I then roll this crazy unfair die with another die? Of course I could. I just did that. Suppose I rolled a fair 6-sided die with our crazy 11-sided die. What would be the result? It's the same probability distribution as if I rolled 3 fair 6-sided dice. In other words, if I do the computation for rolling 2 fair dice, and then think about that as one crazy unfair die, and roll it with another of my fair dice, I would get the result of having 3 dice thrown. In other words, if I wanted to roll 15 dice that were all the same, I would compute the probability distribution of throwing 2 of them. Then I would take that result and I would throw with another fair die. I would take that result, I would throw another fair die. I would do it 15 times. This is of order O log n. We can deal with that kind of computational complexity. Here's the result of rolling 15 6-sided dice. Notice it really does look like a normal curve. It really is the central limit theorem in real life. It actually works. All right, so we know about throwing dice. I said we were going to talk about multi-tenancy and oversubscription, right? We're good at throwing dice, but how does that apply? Here's a graph. This is the job efficiency, so the efficiency is down here on the bottom, and the probability of each of those job efficiencies when I look out across my farm. This is not the number of jobs at this efficiency divided by the total number of jobs, because jobs have unlevel efficiency during their runtime. What this is instantaneously looking at my farm, measuring the efficiency of every job that's there at that instant in time, and then repeating that process billions of times and computing a histogram. A lot of efficient jobs, a lot of really not very efficient jobs. So I have a probability question for you. What if we were to pick 2 jobs at random from that histogram I just showed you and put them on a 2-core server? What if I were to pick n of them and put them on an n-core server? The utilization of that server would then be the sum of all of the efficiencies of those jobs that we just picked. But holy crap, that's what we just did with dice, right? I roll n dice, and I'm interested in the sum of the faces. So if I just simply pretend that this is one crazy 101-sided die, and ask myself what happens when I throw it in times, I actually get an approximation for the utilization of the server. Here are some examples. Of course, if I only do 1, I get the probability distribution back. If I throw 2, look, the most likely thing is I picked 2 high utilization jobs. The second most likely thing, I picked a low and a high. And then down here is 2 low utilization jobs. Notice the mass is starting to hump up. If I do 3 jobs on 3 cores, it's a bigger hump. I got 3 peaks. By the time I do 4 cores, it's starting to get really humpy. If you keep doing this, it'll start to look like a normal curve. And if you're good at stats, you can actually avoid some of the computation here with large numbers and use the central limit theorem. I told Derek there was no calculus, but I lied. So here's what happens if we do 5 jobs on 4 cores. The utilization, some of it is over 100%. You can't have a utilization over 100%. So what does that mean? It means the server was overloaded. That's bad. Server overload means some of the jobs that I'm running will run slower. Well, what's the probability of that server being overloaded? It's the area of the pink part divided by the area under the curve. So it's just Calc 1 this time. Or you can just think about adding up all the bars if you're a computer scientist. So this gives us a way to ask the question, what is the probability that a server will become overloaded at different levels of oversubscription? What do we do with this? We do it for a bunch of different examples of slots. So we take a 16-core server and we say, what's the probability of being overloaded if I run 16 slots there? Well, it's nothing, right? What if I run 17 slots? I get a little sliver of pink. What if I run 18 slots on a 16-core server? Well, I get a little bump. How about 19? Well, it's a bigger bar. If I run 20 slots on a 16-core server, I get this gigantic bar, but oh, wait a minute, it's 5%. So if I run 20 slots on a 16-core server, given that efficiency data that we just looked at, I only have a 5% chance of that server being overloaded. So 95% of the time, my servers won't be overloaded. Now, I said we were going to compute risk. So far, we've computed probability. It's just how likely is it to happen. But risk, the way that accountants and actuaries and casino owners like to look at it, is the product of that probability that we just computed times the cost. I don't know what the cost is going to be if a job runs long, but I can proxy that with that runtime number. And when I go to my bean counters, I can say, you know, if we oversubscribe a system by a particular percentage, then we'll have about that same percentage of slowdown on jobs on average. It's actually not true if you set your C state, P states funny. So at the end of the day, what I can say to management or my actuarial team and my company is that we could get, say, a 20% improvement in throughput, and this you can actually put a dollar figure on. What I usually do is I take the cost of getting all of those cores in AWS and say to management, It's this many millions of dollars of free compute we'll get, and the cost of that free compute will be 4% of the time an angry engineer will call someone up in my management chain about their job running 15% slower. Generally speaking, my management chain doesn't care about it anymore because it's $10 million worth of free compute. I give them this table for all of the possible slot numbers that they have. They send it off to the business analyst team and they decide. They pick a level that they like. So, the FAQ. So these are the questions that people have been asking me when I give them this over the phone when they call me in the last year. They're like, okay, so all I got to do is just think about rolling dice and that sets my oversubscription level. Well, not always. So for about 80% of the people I've spoken to in the last year, it does actually set it for them. I mean, they don't need to do anything else. But if you've got a complex cluster, if you've done crazy things with your distributed resource management tool, or if you've got a lot of diversity in your farm, maybe you've got a bunch of analog engineers and a bunch of digital engineers, and their jobs don't mix any better than the people do. You may have to do what TI has done and take into account the queue structure that you've got and your LSF scheduling parameters. We're an LSF shop. You may also have to take into account job arrival and resource requirement patterns. We have some crazy jobs that do not play well with others. If they mix on a host and they overload the system, one of those jobs will run at 20% and the other will run at 90%. If that job wasn't there, the first one would run at 100%. Those jobs just don't mesh well with each other. And so we've done a little bit of work to isolate some of the worst of those jobs, put them onto heavily oversubscribed systems so that they can run free and happy, and keep the other ones separate. But in general, what this means is that when I think about the probability question, I don't say, do I pick in jobs at random from that distribution? I say, I pick in at random given some constraints. And so my probability question is just a little more complex. If you're in that unlucky 20%, you'll have to do this. If you're not, you won't have to do any of it. How do you tell if your model works? One of the best ways is to do what we just did, and you have just computed a histogram of CPU utilization across your farm. Go measure your CPU utilization in your farm. If the two match, you're probably in the 80% group that doesn't have to do any more work. If they don't match, you should be doing some principal component analysis and trying to figure out what things made it not work. Another really cool way to tell if your model works is simulation. If you're an LSF user, you can actually buy a cluster simulator from IBM. You can write your own. That's what we did. Just take your log files, put a new configuration into the simulator, run it through the simulator, and see if the simulation matches what your theoretical computation was. If it does, you're probably golden. Mitigating the risk. Actually, most scheduling tools do a really good job of this. Use R1M, R15M, and CPU utilization. Don't run a job if they're over the thresholds. And most of the time, maybe 99% of the time, your DRM tool will stop those overload scenarios. If you're scheduling jobs sequentially, it will almost stop them every time. If you're doing multiple dispatch at a time per interval, you'll have a few times where you actually do get some overload. But in general, you can have your DRM tool fix a lot of the overload conditions. How do I tune and monitor it after the fact? So once you start loading all these jobs up on a system and they now interact with each other, you can no longer measure that histogram we had early in the presentation because they will be interacting with each other and they'll change the histogram. The answer, keep a statistically significant sample of machines in the old configuration in your farm. In fact, put some in alternative configurations you're considering. On top of that, run in situ benchmarks where you just fling known benchmarks across your farm randomly. Statistically analyze the results of those benchmarks and keep track of what happens on your test machines, and you can tune it and redo the computation in the future if you want. You can also remember that in any farm, no matter how well made, there will always be a bunch of cases where even if you've got your slot threshold set to 20 on 16 core servers, there will be a lot of instances where you only have 16 jobs running on those 16 core servers. Those are also a statistically significant sample in your farm that you can use to then judge whether or not things are working. The last fact, which is not here, is machine learning. Can you use that instead of a manually done analysis? You absolutely can, and we've done it in TI. The first time I did it, it took 2 weeks for the model to actually run. Inside of it, I used some tools to break apart the neural network and look at what the node weights were and how they worked. And I found inside the neural network a representation of the probability distribution I showed you earlier for the first part of the histogram and the last part of the histogram, and nothing for the middle, which told me that the neural network had actually computed that histogram and was using it in the model. So when I did it the next time, I actually fed it those probabilities directly. My training time went from weeks to hours, and the model was more accurate. So even when I used pure machine learning, it ended up solving the problem largely the way that we had done it by hand. I don't know if that was luck or if that's just the most expedient way for a neural network to do it. Questions?
So in your example, you only showed what looked like, a little closer, what looked like jobs that basically only run at 100%. And that if you had 4 cores, you would request a job that only, that would fit on a 1/4 of that in memory.
Mm-hmm.
So how does that play into it? Or
So memory is a big deal depending on how you buy your resources. In Texas Instruments, we actually do something quite silly that solves the problem. And that is we buy an enormous, crazy amount of memory for each box. Each box has, in fact, so much memory that any job could run on there. I think right now we're doing like 16 cores and 256 gig or 300 gig of memory. And bigger when we're, I guess in the future we're going to do 700 gig of memory on 16 core boxes. So yeah, we just buy freakishly amounts of memory. That is not what I would suggest you do if you don't want to spend all that money on memory, though. Right? And the answer is the same way. You compute a histogram of memory sizes for your jobs, and you ask yourself, it's memory sizes on one axis, CPU utilization on the other, and then you pick randomly from there, put them on machines, and see what the chances are of you being overloaded in memory or overloaded in CPUs. And you can do the same technique. But we haven't had to because we just buy too much memory. We do the same thing with disk drives too, /temp, things like that.
Excuse, I joined a little bit late, so sorry if you answered this earlier. But our primary pinch point appears to be memory bandwidth. And that sort of dominates everything.
Yeah, and it's insidious because when you measure idle time of jobs, it doesn't show up.
Yeah.
It actually shows up as CPU time. So you can be spending all your time because your cache is completely incoherent. You're waiting for memory, and it shows up as CPU time. Yeah, we've spent the money to buy the Intel tools to watch our jobs and see how often that happens. And it happens a lot, especially with analog tools, because there's so much quad floating point precision. It turns into not an FPU problem, but a memory bandwidth problem. We try to segregate those jobs.
Even digital sims.
Yeah.
Yes,
this is true.
It just makes the problem even harder.
Yep. And what you'll see, and it actually shows up in the benchmarks when you watch it happen and you've done oversubscription, you'll see really high CPU utilization in the job slow down from what the benchmarks were. And those in situ benchmarks point those things out really, really well. And once you get a big arrow pointing at them, you can talk to the engineers and say, hey, we would like to isolate you because you're special over here.
Thank you.
But yeah, it's a tough problem to solve.
Question? Any other questions?
Mueller?
Bueller.
Bueller.
No, Mueller's a different thing
I know,
altogether.
but it's, more politically interesting.
Thanks a lot, Mitch.